Okay, so we ended off on Friday discussing how the Arrhenius parameters were determined for a chemical reaction. Well, quite often those are determined using they're quite often determined empirically. There are some really advanced reaction rate theories that you can use too, and also molecular dynamics. But the most common way is to use some sort of shock tube apparatus or a rapid compression machine. But the idea between the both of them is sort of roughly the same. So you have a test section here. You fill the test section with a gas of your choice. It's typically a gas that you would want to test a chemical reaction on. Like say if you want to test hydrogen plus hydroxyl, you would find a way to basically isolate that reaction. And then they want to study how fast those species react at a given pressure and temperature condition. So then what they'll do to create that pressure and temperature condition, they'll use a shock tube. And a shock tube is just a device there's initially a diaphragm right here, and you fill a driver section with high pressure gas, and you fill a driven section with a low pressure gas. Then at the start of the experiment, you basically rupture the diaphragm, and that sends a shock wave into this driven section here. Okay, so that sends a shock wave. That shock wave reflects off of the back wall, and in this sort of doubly shocked region here, you have high pressure, or you have higher pressure, higher temperature, stagnant gas nominally. And so basically, this here is your sort of this here in the region behind between the back wall of the shock tube and the reflected shock wave. That is the test condition. And then so basically in the test section, then they have various diagnostics to measure species concentration as a function of time, pressure and temperature, things like that. And so basically this device, by controlling what gas you fill in the driven section here, and also the ratio of the temperatures and pressures in the driver and driven sections, within a range, they have very fine control over the pressure and temperature that they can monitor the progress of a reaction. So then, assuming they have high quality data and they can measure any variable that they could ever want, how do they then determine the forward rate constant and the Arrhenius parameters? So basically, how is this fitting done? Well, it depends on the reaction. So let's just consider a first order reaction here. It's just a generic reaction. It's A2, goes at some forward rate constant to 2A. Okay, and I didn't mention reaction order earlier, but you could consider that reaction order N is the sum of exponents on the concentrations in the rate of production. Okay, so if we so for basically the rate of production for A2 is negative because we are destroying 1 mole of A2 times Kf times the concentration of A2. So here the sum of all the concentrations are of the exponents on all the concentrations here is 1. So it's a first order reaction. If we go all the way up to the global reaction, we had this. So here, the overall reaction order would be the sum of the exponents. So it would be N plus M. And so that would be the overall reaction order. And yes, I realize N is being used twice, but that's just common notation. Okay, so let's say we are measuring, we are trying to determine a rate constant and the Arrhenius parameters for basically for this chemical reaction here. So if you are to determine this rate constant, you first need to assume a model for the reaction. Okay. And so here we'll just assume it's a first order reaction like this, and you can add complexity to it if needed. Okay, and so now what we do then is let's just pretend that the rate constant is constant, assuming constant rate constant. That's too many constants in 3 words, and you integrate, basically solve the ODE. Assuming an initial concentration of A2 as A2 naught, it's a rather simple separable ODE to solve, and you get that the time varying concentration of A2 is equal to the initial concentration times this decay function here. Okay, or we're sort of, so here this is if you wanted to know or predict the concentration of A2 as a function of time, you would use this form. But here, what we are looking for is a way to deduce Kf easily from experiments. And so you could, in principle, just do an exponential power fit, and then Kf would be the coefficient inside of would be the coefficient inside of the exponential. But we can actually do this quite a bit smarter, because some software can have a difficult time fitting power laws, or even if you have a more complicated reaction, it may be more complicated than even this. So instead, what we can do is we can take the log of both sides and divide both sides by the initial A2 concentration. And by definition, since the reaction is depleting A2, the initial A2 concentration cannot be, it has to be greater than 0. If it's equal to 0, then the concentration of A2 is always equal to 0, which means you didn't test the reaction. Okay, so if we do that, we have this log of A2 over A2 naught is equal to minus Kf times time. So what this is telling us is basically, this is telling us how to plot our data and fit the data to directly find Kf. So basically what this is saying is if we plot the logarithm of A2 over A2 naught as a function of time, like this, it should be decreasing with time, which makes sense. But also, if you do a best fit line, the slope of that line will be minus Kf. Okay, so this is basically saying if you have a chemical reaction like this, the way that you would find Kf is the way that you would find Kf is by basically fitting data of A2 over A2 naught as a function of time. And then the slope of that line would be minus Kf. Now, what happens if you see that the data is not statistically a straight line like this, but there's some sort of significant curvature? Well, that would usually indicate that usually indicate one of two things. The primary choice is that your chemical reaction that you assumed here is incorrect. Okay, and so then you need to go back to the drawing board, propose another reaction, and go through the same procedure. And you may have to plot something different. Or the other thing that it means is that maybe in your experiment, the temperature was not as well controlled as you thought it was. And so then Kf itself is changing as the reaction proceeds. And so that would also produce a strong deviation from this line. So if you are fitting rate constants to data, you need to pay really close attention to sort of details like that. Because if the model says it should be a straight line and you have significant curvature, or it's doing something different, then that usually means that your model is wrong, and you should question fitting it. Okay, so Now we have Kf. Now how do we find the Arrhenius parameters? Well, the traditional way to do it is to make what's called an Arrhenius plot. And so this can be used to deduce the prefactor and the activation energy. So assuming Arrhenius kinetics, which means we assume that the rate constant is of an Arrhenius form, we can assume that that the Fourier rate constant is a prefactor times temperature raised to an n, yet we have a third n here in 5 minutes, times an Arrhenius term here. And remember, this Arrhenius term is just the fraction of successful collisions that promote the chemical reaction. Okay, and so for the sake of example, we'll just assume that the temperature exponent is 0. And so if you assume that the temperature exponent of 0, you can take the log of this expression here, and you get the log of Kf is equal to the log of A minus EA over RU times 1 over T. And so this is telling you that if you want to find A and EA, what you do is you plot the log of Kf versus not temperature, but the inverse of temperature. And then if you plot that, basically on a log A or on a log Kf versus 1 over temperature, this should be a straight line, and the y-intercept will be the natural logarithm of the prefactor, and the slope of this line will be minus EA over the universal gas constant. Okay. Okay, and so this is called an Arrhenius plot, and they're used all the time. And so you can, and they're used in other contexts too, is that you may not necessarily plot a rate constant as a function of say 1 over temperature, but it's generally means if there's an Arrhenius plot, you're plotting the log of some quantity versus 1 over temperature. And if that's a straight line, that's usually indicative of there's some sort of strong Arrhenius like term that is governing something. For instance, for particle combustion, you can plot how long it takes the particles to burn as a function of 1 over T. And often if you do that, even though it's not a Fourier rate constant, you will see that in some regimes there will be a perfectly straight line. And so even in that context, it's called an Arrhenius plot. Okay. Okay. So then a procedure for finding Kf and all these Arrhenius parameters would be to do a series of experiments at basically various pressures and temperatures, and then find a Kf as a function of pressure and temperature. Then after you find Kf as a function of pressure and temperature, it should be independent of pressure, hopefully. If not, that is indicating something else that I'll get to in a few minutes. Then you take that Kf as a function of temperature, make an Arrhenius plot, and then you're off to the races finding your best activation energy and best prefactor. Okay, and if you see curvature in this line, but your Kf data fits, that basically means that you should consider adding this temperature exponent term here. Okay. But often you can find EA and A directly, and so you can use the analytic solution to your chemical reaction system to fit the activation energy and the prefactor directly. So if we define a characteristic time, I'll call this tau 1 over E. It's normally called tau car or tau car, but but basically this is defined as the time when the ratio of the concentration of A2 divided by the initial concentration of A2 is equal to e raised to the -1 power. This one's used quite a bit in chemistry because it makes math super easy, as you'll find here in a few minutes. Another common one would be tau 1/2, and that's the half-life. And so, which you may have used in high school and also college physics and things like that. It's the same concept, except for tau 1/2 is just this concentration is equal to 1/2 rather than e to the -1. And it makes the math slightly more cumbersome, that there's all sorts of exponentials and sort of logarithms that you need to consider. If you use this definition, it disappears and becomes quite nice. So basically, if you use our analytic solution, which is right here, we can show that tau 1 over e is just equal to a 1 over kf. Okay, and then we know that it's directly just 1 over kf, so that's 1 over the prefactor times e to the minus EA over RUT, or we can basically we can make an Arrhenius plot of the characteristic reaction time, tau 1 over e. And so if we do that, we find that the natural log of tau 1 over e is equal to minus the natural logarithm of a plus EA over RU times 1 over t. Okay, and so if you have KF data, you don't need to go through the step of finding KF. Is that basically you can use the solution and our definition of the Arrhenius term, or of the Ford-Ray constant, and basically find A and EA directly. And so basically what this is saying is you plot the log of the characteristic time, which you measured in the experiment, or you can deduce fairly easily. And then the slope will be positive EA over RU, and the y-intercept will be minus the natural logarithm of the prefactor. Okay, and so you can play a bunch of games like this if need be to find all of the Arrhenius terms and things like that. Okay. So issues to look out for, you guys will be getting a homework problem, and I will be posting a new homework sometime this afternoon. And issues to look out for when you are fitting reaction models. It's best to find, in my opinion, when you go through this, at least for homework problems, it's best to find an analytic solution to the reaction model. And look for that solution. That solution will tell you exactly what to plot and what the slope and intercept will physically mean. And you can do this. I did an example, the sort of simplest example that there is with the first order reaction, or one first order reaction. You may have multiple reactions that you need to consider. And so for systems, to get the analytic solution, you may need to use techniques such as Laplace transforms to solve a system of a series of differential equations resulting from the rates of production. And then also pay very close attention. What? It did not bump Siri, but it's going nuts on ODEs. This is weird. A boomer moment, I guess. But then also, go away, Siri. What are you doing? So then you should pay close attention to details of the ODE solution. So for example, sometimes you will find that your ODE solution will predict that basically the quantity that that you are plotting, it will predict that that maybe the y-intercept here is not minus log of A, but it's exactly 0. And the theory predicts exactly 0. And so, but yet, if the data shows that it is significantly far from 0, that usually means that there's something wrong with your chemical. That's something wrong with your proposed reaction model. And so, pay attention for like things like that. Look for things like the slope of the line being in the wrong direction, or the line being significantly curved, things like that. And so, if those details are violated, such as the y-intercept detail, you may need to add a reaction or change to a different rate constant model, or add or remove a reactant to sort of get it to work out. And so these are games that the chemical kineticists play all the time. And you would think that these in combustion are done primarily by chemists or chemical engineers. Actually, these are done by mechanical engineers. Chemists and chemical engineers tend to work on low temperature chemistry. And by low temperature, I mean like normal room temperature stuff, or at most to them, high temperature would be like 500 C. 1,000 C is crazy high for them. And so for combustion, the chemical reactions at high temperature are different. And so mechanical and aerospace engineers tend to be the people who actually develop these chemistry mechanisms for our applications. So now, one thing that I need to discuss, because you see them quite often in reaction mechanisms, are third bodies in pressure-dependent reactions. So a third body is an inert molecular collision partner that is needed for an elementary reaction to proceed. So consider, and a third body is given by a symbol M. And this M represents any collision particle. In theory, it can be any species. It doesn't matter what it is. It just needs to be something. So let's consider H2 plus M, which is that M is indicating a third body. And then that's gonna break the H2 into two H molecules. So why this is needed is, just consider we have our H2 molecule just happily sitting there doing nothing. And let's just consider this chemical reaction without the third body. So the chemical reaction is now like this. Do you expect that if you have an H2 molecule that's happily sitting there, do you expect it to just spontaneously fly apart by itself with no additional energy input?
That would be a fun world if so.
Yeah. No, so that just doesn't happen in real life. Is that something provided? Basically, something gave this H2 molecule enough energy to break itself apart, and basically often what gives it that energy is a third body. And so what this third body does is it's a collision partner. So you could think of it, again, all chemical reactions are a giant game of billiards. So you could imagine you have these two H atoms, which are connected by something that you could think of as a spring. And now you need to break that spring or that chemical bond. And one way to do that is, again, to have any molecule basically crash into this H2 molecule, and if the collision energy is sufficiently high, there will be enough energy to basically break this bond. And if M and H do not react, that is, a bond does not form between M and H, then you wind up with three fragments. You basically wind up with M, which is you could think of as an impactor, and then you wind up breaking apart the H2 into two independent H atoms. Okay, and so this happens all the time. And this third body, it's any collision partner. In theory, it can be any molecule whatsoever. And so this M provides the additional energy that is needed to break apart H2. But also, if you are to think of this chemical reaction in the reverse direction, so we have two H atoms, and we have a third body. Well, in the reverse direction, you also need a third body collision partner for the exact opposite region. So these H atoms, there's like much of the time, there'll be enough energy in both of these H atoms that if they come together and start to form a bond, there'll basically be so much energy in that H2 in that H2 molecule that is formed, is basically it'll almost fly apart right away, right? And so there is essentially too much energy in these two H atoms. So what is needed then is you need a collision partner to actually scrub off some of to basically scrub off some of that kinetic energy. And if you remove some of that kinetic energy, then the H2 molecule basically it can be stabilized and it won't fly apart. It won't fly apart right away. Okay, and so basically, that you can argue that for a lot of these for a lot of these for a lot of these decomposition type of reactions where you are breaking apart a molecule into two pieces, presumably by itself, they often need some sort of third body. And the argument can be made that you need the third body in both directions. Okay. So now one thing to note about a third body, it's an inert, is that it does not change from one side to the other. And then also the third body does not affect chemical equilibrium, because if you remember that there was a Kp term, and the delta nu this is that the change in moles of M is 0. Okay, so if you were to go back and do chemical equilibrium, this third body would have no direct influence on chemical equilibrium for say for this chemical reaction here. Okay, and so for the third body concentration is that you can use the law of mass action, and so the rate of production would be Kf times the concentration of H2 times the concentration of all the third bodies. And so the concentration to use in the law of mass action for the third body, Cm or m in square brackets, is the sum of alpha I times the concentration of all the species. And this alpha I is called a third body efficiency or a chaperone efficiency factor. And these parameters, if any of you have played with Chemkin or Cantera, these are the parameters that are often given by chemical, or that are often given with chemical reactions that have a third body in them. Okay, and by default, if you're looking at a mechanism and it has a third body and it does not list a species efficiency factor, it's by default unity. And so let's see, I think I have one over here. Yeah, I have a third body right here in this chemical reaction. And so for this chemical reaction, the efficiency factors for all species are 1. But that's not always the case. Let me see if I have.
So Professor, wouldn't that efficiency factor be a function of temperature? Or I guess once you reach a certain temperature, you may be able to consider that as unity. But at some point, you know, some collisions may not have enough energy to break apart the molecule.
Yeah, and in principle, it's the Ford-Ray constant term that takes care of that. In reality, these chemical reaction mechanisms and the rate models, there are a lot of empirical curve fitting, because as you just brought up, there's a lot of really physical details that they do not account for, because it'd be really complicated to account for all of those details. And in principle, since the third body is a collision partner, in theory, the efficiency factor for all of the reactions should always be the efficiency factor for all species should always be should basically always be one from a basic theory point of view. And here I just have a chemical reaction mechanism open on my computer for a code called ChemCin. Let me see if I can make it bigger view. I think I can do it like this. Can you guys read it, or is that way too small? Oh, here it is. Okay, so here is a mechanism for, I think it's for a mixture of methane and ethylene. And so this is called a ChemCin file. Again, here is a chemical reaction string. This is a third body reaction right here. This would be the prefactor, the temperature exponent, and the activation energy in cals per mole. And so you see in this string down here, you see this H2/2, H2O/0, etc. These here are actually how in the ChemCin file, which is a very standard combustion chemistry code. This here is the efficiency factor for H2 for this chemical reaction. This is saying that H2O for some reason has a efficiency factor of 0. What I'm guessing is that if H2O is the colliding partner, it will actually react with this, basically rather than act as an inert collision partner. And so if you are looking at a ChemCin file, you can basically see this. Do I have a Cantera file open? Let me see. Yes, I do have a Cantera file open. And then I will be going over Cantera later on. Let me see. And so for a Cantera file, they're a bit more straightforward. So here we have a chemical reaction here. It's 2O plus M goes to O2 plus M. In a Cantera file, these three parameters here are the prefactor, temperature exponent, and the activation energy. This has an activation energy of 0. But here you explicitly list these here are the third body efficiency factors. Okay, and you can notice that these are not necessarily all close to 1. Say for like basically some of them are say 15 points are over 10, and so yeah, under the hood at the molecular level, there's a lot more going on than just H2O. In this case, is an inert collision partner. If its collision efficiency is 15 times higher than theory, then there's something sort of kind of wrong with the basic theory. But this stuff is actually very complicated at the molecular level. And so you can view all of these as sort of empirical curve fits are basically empirical fitting parameters to data. And because if you notice that you have the prefactor, the temperature exponent, the Arrhenius or the activation energy, third body efficiencies, is that chemical reactions there is a whole lot of empirical fitting to these. So be very careful if you're using a chemical reaction mechanism, is that if you are, say, modeling the combustion inside of a rocket, which could involve supercritical combustion of liquid oxygen, and for that you'd use like Peng-Robinson is a very common equation of state to use, and you're looking for a chemical reaction mechanism to use like this, you would not look for one that was tuned for, say, gas turbine combustors. It's a completely different combustion regime, and because of all these different fitting parameters, is that they may be optimized differently. So you just need to pay very, very close attention, very close attention to that. Okay. And then also another thing to look out for in these reaction files are called pressure dependent reactions. In the other combustion class, I go through, it takes about 1 to 1.5 lectures to actually derive these in detail. So I'm not going to do that here. I'm just going to tell you what the results are, is that these are chemical reactions that change their reaction order as a function of pressure. And so basically at high pressure, the third body effect here can actually be very important, because you could think of is that the rate of production in the reverse direction would be H times the concentration of M. And so this here would be proportional to pressure raised to the third power. So basically this, the third body raises the dependence on pressure by increasing its exponent by 1. And so at high pressure, the effect of the third body is very important. And at low pressure, for basically some reactions, the effect of the third body is weak, and then the chemical reaction behaves like this third body just doesn't exist. Okay, and so that only occurs for basically some reactions, but not others. But they are very important to chemical reaction mechanisms. And so these reactions are denoted by putting the third body inside of a parentheses. So we have H2 plus O2 plus M inside parentheses. And so basically what this means is that the M is important, is you treat this as H plus O2 plus M at high pressure, and you treat this as H plus O2 at low pressure. Okay, and I'll show you the mechanism file here, and there are a set of Arrhenius parameters for both these high and low pressure limits. And so we need to think of, well, we have this one reaction, but it's sort of acting in two different ways. How do we determine a net rate of production for this and a net rate constant? Well, there's a theory called Lindemann Theory, and again, I'm not going to get into that here. If you're interested, it's discussed in detail in Ken Kuo's combustion book. And this Lindemann theory predicts that the net rate constant is the high pressure rate constant times the low pressure rate constant times the third body concentration divided by the high pressure rate constant plus the low pressure rate constant times the third body concentration. Or you can view it as you could view Knet as the harmonic average between the high pressure rate constant and the low pressure rate constant multiplied by the third body concentration. Okay, and so that's basically what this expression here is saying. And so using this Knet, the rate of production of, say, H would be dH dt is equal to minus this net rate constant times the concentration of H times the concentration of O2. And if you're at high pressure and the concentration of M is important, that will that M will be taken into effect by a net rate constant. Okay, and so these are just these are chemical reactions that you need to look out for, and then in conferences and things like that, you will hear people talking about trough-fall reactions. So these are sometimes called pressure fall-off reactions, and this blending here from basic theory, it doesn't fit data very well quite often, and so there's more empirical blending, and I'm not going to get into those. And the so-called trough blending is actually more often used. And so an example of a so-called trough fall reaction is right here. It should be multiple. It's got its full one. Yeah, here's one. Here's a fall off reaction. So this is called a pressure fall off reaction. We have O plus basically plus a plus carbon monoxide, and that nominally goes to CO2. And then at high pressure, the third body effect is important, and at low pressure, it's not important for this reaction. Okay, and so here we have our two sets of rate constants, and we have our efficiencies. And now note here, it's not listing any Tro parameters. So this here is using, so basically this reaction here is using Lindemann blending, which is the exact expression that that I showed on the slide. Let me look for one that has Tro. Yep, here's one that has Tro blending right here. Okay, and so notice that here it's the same, except for there are extra basically Tro parameters, and then that's basically that's basically controlling how the low pressure rate constant and the high pressure rate constant blend together, and so it's just a way of doing that. And then so this is a Cantera file, which you guys will be using, and I'll just show you a Chemkin file because you will encounter those a lot in your if you work with combustion. And in a Chemkin file, here's one right here. So we have we have CO plus H2 plus M. And so that's here, the M is in parentheses. So that is indicating a pressure dependent reaction. And so here is a set of Arrhenius parameters for the high pressure limit. Here is the set of Arrhenius parameters for the low pressure limit. These are the third body efficiency factors for the third body. And then here are the Tro blending parameters. Okay, and so those are quite, and so you do see these quite often. In my own code, we had a bug in actually one of these, and even though for hydrogen it influenced one reaction, it was enough to screw up flame speed, or to basically screw up calculations by about 50%. Even though these pressure dependent reactions are pretty important to a lot of combustion mechanisms. Okay, and so that's all I'm going to go over for chemical kinetics. Do you have any questions?
Yeah, I have another question about these efficiency, the efficiency terms, the alphas.
Mm-hmm.
Let's see here, kind of lost my train of thought. So a lot of times you may be trying to analyze a new reaction, or say you're always adding something in. Is there a way to predict what these efficiencies are going to be if you can't look it up in a table? I mean, it seems like the efficiencies change for each species depends on, what reaction they're in. You see H2O change depending on what you have it coupled with. So say I've got a reaction I can find in a book somewhere, and then I want to add, aluminum to it, or I'm adding something to it that's no longer in the book. How do I adjust my efficiency factor, or how do I know?
There is no theory to do that. The theory predicts 1 for the efficiency factor. So say you're doing hydrogen oxygen a combustion with aluminum, and because aluminum can burn with say water vapor. So it's a pretty common thing that you basically want to do, is that you would want to take a hydrogen combustion mechanism and add in the aluminum reactions. So if you were to do that, then in these three body reactions, or in the third body efficiencies, you now have all these extra aluminum species to deal with. And so what are the efficiency factors of those? By default, you would just assume 1 if there's no theory, if there's no experimental data for you to fit them with. And basically how these are fit is, it's kind of kind of crude in a way, is that there's no basic theory to basically give you the 15.6 or whatever it is. Essentially, what they do is the chemical kineticist will basically twiddle with them to get to get bulk combustion phenomena to match experimental data. So we'll be going over, say, laminar flame speeds here in a few weeks, which is just the same thing as a propellant burning rate. And so what they'll do is they'll basically twiddle with these efficiency factors until they get decent fits to basically improve the quality of the chemical reaction mechanism in predicting things like an ignition delay time or a laminar flame speed. Okay, and we'll be talking a little bit about ignition delay time here in a tiny bit too. So no, these are done all empirically by sort of the chemical kineticists.
Gotcha. And then
Okay.
kind of the last thing I'm understanding, it's called an efficiency factor. And usually I think of that as an efficiency, it's like from 0 to 1. But we have these factors here that are like 16. And so I was thinking of these efficiency factors as like, if it was efficiency factor of 1, then every time molecule M interacts with H2, it always breaks it up. Yeah, but if I then take that to 15, I don't know how to think about that.
Yeah, no, it is poorly named.
Okay.
It is.
So it's really they're just using it as a knob to turn to fit the graph.
Yeah, and I think from a basic theory point of view, you could argue that this alpha I shouldn't, in principle, be between 0 and 1.
Okay.
Right, but then you find some like to get the reaction mechanism to fit the data, you sometimes need these alpha i's to be 15.
Gotcha.
So basically, like I said, for these chemical reaction mechanisms and mechanism development, there's a lot of empiricism to them, and then also in combustion, because I know for what the hell was it? It might have been for RDX combustion. I think Rich Yetter was involved in the development of those, and he got some of the chemical reactions from garbage incineration. So he had to take parameters from a completely different field and then map them to say a completely different field in propellant combustion. And so he had to play a lot of these games too to get this all to work out. And also for your guys, for a computer project, you will be modeling propellant combustion. So, but that's a great question. But yeah, so no, there's a lot of empiricism to these reaction models.
Okay.
Okay. Any other questions? Okay, stop recording.